Recall that we learned a short method of multiplying together two complex numbers. Anytime we had complex numbers in trigonometric form, we simply multiplied together the radii, and then we took the sum of the two angles. Well, considering exponentiation, the process of applying exponents to a number, is really just expanded multiplication, then there should be some similarity between multiplying and raising to powers. So let's just start off by raising this number to the power of 2. We expand this out and multiply, we're really just multiplying by itself. So in applying this formula, we're multiplying the radii, and now we're adding together the angles. So we get theta plus I times sine of theta plus theta. And so if we were to simplify this, then that simply becomes r squared times cosine of theta plus theta, which is 2 theta. Now I wonder if there's going to be a way for us to be able to think about this. If the exponent is 2, it looks like all I did was squared the radius and then multiplied the angle by 2. So let's just see if we could continue this and maybe try this with the power of 3 and see if we get something similar. If we're going to raise this to the power of 3, we're obviously going to have to multiply this complex number by itself 3 times. So we're going to multiply r cosine theta plus I sine theta times itself 3 times. But keep in mind that we've already found the answer if we multiplied it together twice. So why don't we just take our result and multiply it by r squared, and I realized I did not finish this up here, shame on me. This becomes plus I sine of 2 theta. Okay, so notice that what we've done here is we've just simply squared squared the radius, and we've doubled the angle. So now let's multiply by this complex number, which is r squared cosine of 2 theta plus I times sine of 2 theta. And we'd be able to do the same process even with a power of 4 or a power of 5 or 6, as long as we continue to find a few of these powers. And so if we were to multiply these together, notice this gives us r times r squared. We're still multiplying trigonometric form. So we multiply the radii. And now we multiply by cosine of the sum of the angles. But now the sum of the angles is theta plus 2 more thetas, plus I times sine of theta plus 2 theta. So it looks like there's another shorthand notation for raising the powers, because this power of 3 becomes r to the power of 3 times cosine of 3 theta plus I sine of 3 theta. So again, it's no longer necessary to do any intermediate work when we're raising to a power, because if I want to take that number and raise to the power of n, notice that all we've done when we take that complex number to the power of n is that we've raised the radius to the nth power. And now the way that we've changed the angle is simply multiplying the angle by n. And this is what we refer to as DeMoivre's theorem. DeMoivre's theorem is a shorthand notation for how to take powers of complex numbers. This complex number, 1 plus I root 3 to the power of 8. Now, if we want to multiply or raise this to the power of 8, we could do that easily with DeMoivre's theorem if this was in trigonometric form. So the first thing we could do is we could either draw this structure just to see where we are, or we could find our r and theta separately. If we look at the value of 1 plus I root 3, keep in mind that we're saying that for some angle, the x coordinate is 1 and the y coordinate is root 3. Now, because they're both positive, we know that we're in the first quadrant. And secondly, because we see that this is a 1 and root 3 triangle, this means that this is a 30, 60, 90, where this is a 60-degree angle, and this hypotenuse is 2. So from that diagram, we could then see that what we're really trying to do is find what is 2 cis of 60 degrees raised to the power of 8. So we've now just converted this rectangular form into trigonometric form. And because it's in trigonometric form, we're now able to just use DeMoivre's theorem to find the answer. We raise 2 to the power of 8, and then we simply say cis of 8 times 60 degrees. And therefore, this gives me 2 to the power of 8, which is 256, times cis of 480 degrees. Now, it's not customary to keep our angle beyond 360, so we just need to find a coterminal angle to 480 degrees, which means that my final answer is 256 cis of 128 degrees, which demonstrates that if I wanted to raise 1 plus I root 3 to the power of 8, I would have had to multiply that by itself 8 times just to get to the same result that we got here in trigonometric form. But since I was taking a rectangular form and raising to the power of 8, it would still be good for us to be able to convert this back into rectangular form. And so why don't we rewrite this by realizing that the x coordinate is going to be 256 times cosine of 120 degrees, while I'm going to have my I component, which is 256 times sine of 120 degrees. Okay. Well, think about the fact that in the second quadrant, x will be negative and y would be positive. So cosine at 120 degrees is negative 1/2. So we're left with 256 times negative 1/2. And now for our I coordinate, again on our unit circle at the 120 degree angle, it's a steep angle in the second quadrant. So we know that we're going to have sine of 120, which is root 3 over 2. And if I now rewrite that in rectangular form, this simply gives me negative 128, which is the real part, plus 128 root 3 I, which is the result we would get if we were to multiply this by itself 8 different times. So we can see that using DeMoivre's theorem and the product theorem and the quotient theorem, we're able to accomplish a lot of these powers and products and quotients or operations with complex numbers in a much faster way simply by using these shortcuts. And we could actually use DeMoivre's theorem in order to find complex roots of complex numbers as well. And therefore, that means that we could use DeMoivre's theorem to find cube roots or fourth roots or fifth or sixth or seventh roots of complex numbers. And the key to this is to remember that if we have the nth root of a is equal to some number, then by the inverse property, that means that b to the power of n is what gives us a. Which means in this example, we're trying to find all the cube roots, and there will be 3 of them, find all cube roots of this complex number. In other words, find some number, which we're going to name that number, we'll call it x plus yi, right? Or we can call it r times cosine theta plus I sine theta. Okay. So if we're trying to find some number that is equal to the cubed root of this other number, then that must mean something else. It must also mean that if I were to cube both sides, that I would get r cubed times cosine of 3 theta plus I sine 3 theta should be equal to the quantity on the inside, should be equal to 8 times cosine of 135 degrees plus I sine of 135 degrees. So in other words, if we're trying to find a cubed root of this number, then we just define my final answer in terms of r and theta. And when we now apply DeMoivre's theorem by raising both sides to the power of 3, we simply get that r cubed is now going to have to equal 8. And we should also recognize that 3 theta is going to have to equal 135 degrees. So we're just simply finding these cubed roots that are going to make this true. Well, the first thing is pretty straightforward here. We can see already that if r cubed is equal to 8, then that means that the r value is equal to 2. So we've already got the value of r then. So the form of the complex numbers that are the cubed roots of that original value, the r value will be 2. But now we need to find theta. And this is where we've now got to recognize that if 3 theta is equal to 135 degrees, then we can find theta by dividing by 3. The problem is that if we think about this as being cosine of 135 and sine of 135, then we can realize also that any coterminal angle to 135 degrees will work as well. In other words, if we know that 135 degrees is going to be this angle, and we know that the radius out to this point in our real and imaginary axis is going to be 8, what we're trying to do is find the cubed roots of that number. What number times itself 3 times would give me this result? Well, realize that any number that's coterminal to 135 degrees will also give me an answer. And if I take another coterminal angle, that would also give me to the same exact place. And so what we can do then is realize that it's not only 3 theta is equal to 135 degrees, but it's 3 theta is equal to 135 degrees plus 360 degrees times n. Because what we're going to be able to do in order to find this now is divide everything by 3 in order to find theta. But not only are we dividing 135 degrees by 3, we're dividing 360 degrees into 3 equal parts as well, which means that theta is actually going to be 45 degrees, which is 1/3 of 135, plus 120 degrees times n, which implies that if n was equal to 0, then we would get a theta value equal to 45 degrees. But then we could also add 120 degrees once, which gives me 165 degrees. We could also add 120 degrees twice, or 240, to get the theta is equal to 285 degrees. And we could really continue to add again. We could add 120 again and find out that theta is equal to 405 degrees. But wait, notice how 405 degrees is coterminal to 45. So we didn't need to write the value that was beyond 360 degrees, which is why there are only 3 values. And so when we said find the 3 complex cube roots, that's simply because of the fact that when we solve for theta, there's going to be 3 different thetas that make that true. And therefore, the 3 complex cube roots are going to be R1, or rather I should say the cubed roots could be Z1, which is what we refer to as complex numbers. So the first cube root would be 2 cis of 45 degrees. The next cube root, which we'll call Z2, is equal to 2 times cis of 165 degrees. And finally, the third complex cube root is going to be 2 cis of 285 degrees. And so these are our 3 cubed roots, which simply means that if I were to look at these particular angles on our diagram here, we already found out that that was our value, our original complex number. Any radius of 2 is going to be 1/4 the size. So it looks like we're going to be drawing one of the cube roots at 45 degrees, one of the cube roots at 165 degrees, and one of the cube roots at 285 degrees. And therefore we found 3 different cube roots of that complex number simply by recognizing that if this is Z1 and this is Z2 and this is Z3, then these 3 values, if cubed, would get me back to this complex number. And that's how we can use DeMoivre's theorem in order to find not only powers of complex numbers, but also roots of complex numbers. So let's take one more example. We want to finally look at the practicality of dealing with these complex numbers and the sense of how we use this in algebra. So you might recall that there was a theorem called the fundamental theorem of algebra. That was a theorem relating to polynomials that said if you have any polynomial of degree n, for instance, in this case, the degree is 5, then the fundamental theorem of algebra says that there are exactly 5 real zeros to that equation, which means that this equation of x to the 5th minus 1 equals 0 has 5 solutions. And we want to be able to find all 5 solutions. There's a slight problem with that, though, because if we take a look at what this is, if we were to just add 1, this implies that the value we're looking for, if raised to the 5th power, should equal 1. Or in other words, x is equal to the 5th root of 1. The 5th root of 1. What times itself 5 times gives me 1. So you may just think right away that there's only one solution. That's the solution, x equals 1. The problem with this is only one solution. And it turns out to only be the only real solution as well, because the other 4 solutions must be complex roots or complex solutions. So the first thing we're going to do here is to recognize that if we're trying to find the 5th root of 1, what we're really trying to do is find the 5th root of 1 plus 0i. Because if we think about this as a complex number, now we've got DeMoivre's theorem that will allow us to solve this. But you got to be very careful as well, because this would now have to be turned into trigonometric form, which is the 5th root of. And now there's a very simple way, again, to determine complex or trigonometric form if you think about this on a graph. Again, the value, the shape on the graph here is just going to be a real number on the real axis. And so we're just simply going to look at the value at 1, okay, which is out here, 1 unit away, at 1. And therefore, if we think about this in trigonometric form, that's simply going to be a radius of 1 times cosine of 0 degrees plus I sine of 0 degrees. Okay, so we're trying to find all of the complex numbers that make that true. So now we just simply have to set this equal to our unknown result, which we don't know. We're going to say r times cosine theta plus I sine theta. And therefore, if I'm trying to find all the fifth roots of that complex number, then that must mean that I can raise both sides to the power of 5. And therefore, from DeMoivre's theorem, this demonstrates that 1 times cosine theta, or cosine of 0 degrees, plus I times sine of 0 degrees is going to be equal to r to the 5th times cosine of 5 theta plus I sine of 5 theta. And what this allows us to do is find my r value, which is relatively straightforward. We know that 1 is equal to r to the 5th, and therefore that tells us that r is equal to 1. So even in whatever the roots of this are going to be, I know that my answer here is going to be r equals 1. But now I've also got to recognize that 5 theta is going to be equal to 0 degrees plus 360 degrees times n. Remember, the reason for doing so is to find more than just one solution. We already knew that if we divide by 5, we get theta equals 0 degrees. But we already knew that answer. We already knew that answer because this was one of our answers. What we don't know is that if we divide by 5 now, notice that that gives me 72 degrees times n, which now means that we have a few different solutions for theta. One solution for theta is going to be when n is equal to 0, so 0 degrees. Another solution will be when n is equal to 1, so 0 plus 72, which is 72 degrees. Or when n is equal to 2 plus 0 degrees gives me 144 degrees. Plus my next one, if I add 72 degrees again, that gives me 216 degrees. If I add 72 again, that gives me 288 degrees. If I add 72 again, notice that that's going to take me to 360 degrees, which you should notice I don't need because 360 degrees is coterminal to 0. So therefore, these are the angles where the 5 complex roots will occur. So if we now take a look at where those are, let's draw our 3 complex roots. The first complex root is at 1 plus 0i, which we've already drawn. The next one will be 1 unit out at the angle of 72 degrees. The next one will be out at an angle of 144 degrees. The next one will be out at an angle of 216 degrees, 1 unit. And the last one will be out at an angle of 280 degrees, 1 unit away as well. And so what you should recognize is that all complex roots should be 1 unit away. They should all have the same radius. And secondly, all of the angles in between should be equal to the same. And sure enough, they are. This angle is 72 degrees. Add another 72 to get to here. Add another 72 and another 72 and another 72. And it takes me right back to where I began. And therefore, let's write out each of our complex results. All of the complex solutions to this equation are x equals 1 cis of 0 degrees. Or another solution would be x equals 1 cis of 72 degrees. The next solution, since there are 5, should be 1 cis of 144 degrees. The next solution should be 1 times cis of 216 degrees. And finally, the last of the fifth roots is going to be 1 cis of 288 degrees. So look at what we've done. We already had one solution on our x-axis, which was a real number. X is equal to 1 is a real number. But the rest of these, notice, are going to be answers in the complex plane that are not real numbers. However, if I raise them to the power of 5 by using DeMoivre's theorem, I should get right back to a solution that makes this true. So we're going to take one of these answers and we're going to try them. Okay? So let's keep in mind that we were trying to solve x to the fifth minus 1 is equal to 0. Now, one of our solutions turned out to be x equals 1 times cosine of 44 degrees plus I sine of 144 degrees. We'll only do one of these because all of them will work the same way. But apparently that means that if I were to plug that result in and subtract 1, my answer would be 0. So let's give that a try. So let's take all of that, which is 1 times cosine 144 degrees plus I sine of 144 degrees. And we're going to raise that to the fifth, and then we're going to subtract 1. Now, if this is a solution, my answer should become 0. Well, let's apply DeMoivre's theorem. This is going to be 1 to the power of 5. And now I'm going to get cosine of 5 times 144 degrees plus I sine of 144 degrees minus 1. Well, notice that 1 to the fifth is just 1. And now I've got to multiply 5 times 144 degrees, which is going to give me 720 degrees, plus I sine of 720 degrees. But notice where 720 degrees is. That is coterminal to the angle of 0, which means that by our coterminal angles, cosine of 720 degrees is 1, and sine of 120 degrees is 0. So what we're left with inside here is 1 plus 0i times 1 minus 1 is sure enough equal to 0. So now we can see why what this is actually saying is that even though all 5 of these numbers are not necessarily real numbers, there's only one real number that lies on the real axis, it doesn't mean that there is only one solution. There is only one real solution to this equation. However, because of the fact that these other numbers are in the complex plane, there are 4 other complex solutions to go with it. So we can now use DeMoivre's theorem in order to not only find powers of complex numbers in a very simple way, but we could use DeMoivre's theorem to find roots of complex numbers, which in turn helps us to solve different types of algebraic equations by finding the complex solutions to that equation.